Hello, and welcome to this lesson in discrete structures. This is video 2 of proof by induction. In this video, we do two examples, and I encourage you, I'm going to try to give you time to remind you to stop and try each step as we go along and see what you can come up with, particularly for the first one. And for the second one in particular, I'm going to ask you to stop the video and try to fill in the steps yourself. So, proof by induction. Now, often we use this to prove a formula is true for all higher values of a sequence. So we're to prove that 1 squared plus 2 squared plus 3 squared. So actually, if I were to write this out in summation notation, it looks like it would go from I equals 1 to n, and it looks like I'm doing I squared. I'm adding the squares of consecutive integers. And what I'm asked to prove is that this will be equal to the highest integer times that highest integer plus 1 times 2 times the highest integer plus 1 divided by 6. So if I say n is 20, I can just put 20 in for n instead of writing out 1 squared plus 2 squared plus 3 squared plus 4 squared. That's what this means. With proof by induction, I am asked to prove that to be true. So the first step is always the same. Okay, so it looks like we're starting with 1. It doesn't say, sometimes the problem explicitly says for n greater than or equal to 1. Sometimes it might give you the formula and not show you, in a list like this that n starts at 1. So we have to show that the formula works for n of 1. In other words, if I take 1 squared plus nothing else, that would be my only term. If I only go this far in the sequence, then I'm going to get the same thing as if I get when I plug 1 in here. So stop the video, try that. When you come back, I'll do it. Okay, you're back? All right, so I know the sum of just the first term will just be 1. And I want to know, does that equal 1 times 1 plus 1 times 2 times 1 plus 1? And you have to be careful with your order of operations and all this stuff, especially with fractions, over 6. So I have a 1 times a 2 times a 3 over 6. 2 times 3 is 6. Yes, I do get 1. So that first, if it doesn't work for the first term, you're done. It doesn't work at all. So now the second term, assume it works for any n equal to k. We're just going to assume that if I only went up to, something a little less than n, and I'll call that k, it will work. So I'm assuming this will work. So I'll write out the formula for k integers. So that'll be k times k plus 1 over 2k plus 1 divided by 6. Now, what I'm going to have to try to prove is that this plus the k plus first term is equal to p of k plus 1. So if p of k equals that, p of k plus the k plus first term is going to be that plus. Now we have to be careful here because it's not just plus k plus 1, it's plus k plus 1 squared. So this is assuming it works for p of k is this first term here, and then add the next term. And I want to show that that works for when I put k plus 1 directly into the formula up here. So that's k plus 1. N is k plus 1 now. I'm replacing every n with a k plus 1. Now, it'll be k plus 1 in that first set of parentheses. 2, be careful, you need parentheses here, times k plus 1 plus 1. In the third set of parentheses, well, what's the second set in the formula? Over 6. So I'm going to have to simplify that. I'm going to have to use some algebra to show that this is true. What I'm going to tell you here is it's easier to leave the p of k plus 1, this here, leave that alone for a minute and work with step A. So in order to work with step A, I have to get this k plus 1 squared to be over 6. So I have k times k plus 1 times 2k plus 1 over 6. So I'm working with step A, okay? Plus, and I have k plus 1 squared, but I need to write that over 6. So what I do is I say, well, I'm going to multiply it by 1 in the form of 6 over 6. That's how you make a common denominator out of that. You had a 1 on the bottom, you need a 6 on the bottom, you also have to put a 6 on the top. When you multiply anything by 6 divided by 6, you're just keeping the value the same and changing the form. So now I use some algebra steps for this. So that's going to equal k times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared, all over 6. And I'm going to use that little factoring trick I showed you in the first video. It's not really a trick. You should be well aware of this. Look, I've got a k plus 1 factor here, and I've got a k plus 1 factor here twice. So when I can factor that to k plus 1, and the reason I'm doing that is, look, there's a k plus 1 up here, right? Times, I'm going to put just square brackets. They're no different meaning than parentheses in this context in algebra. Times k times 2k plus 1 plus 6 times k plus 1. And that's all over 6. And then I'm going to simplify in here. And I get k plus 1 times, oh, there's a 1 there in the braces. That'll be 2k squared plus k plus 6k. So it'll be 2k squared plus 8k. And if you're confused by that, stop and do it out yourself. 2k times k plus k. Oh, sorry, that won't be 8k. That'll be 2k squared plus a k plus a 6k. That'll be a 7k. Sorry, I almost messed it up on you. Plus a 7k plus 6. Now, look at this. I got this over 6. I've got a k plus 1 here, a k plus 1 here, a 6 here. If I could just show that this up here was the same as this, I would be done. So what you do next is you work up here, because it looks like maybe if I multiply all this out, if I should get this same thing here. So I'm going to work with this here. I get k plus 2 times, so this will be k plus 2 times 2k plus 2 plus 1, 2k plus 3. And if I multiply that out, I get 2k squared plus 7k plus 6. So this is k plus 1 times, so you notice I didn't set up an equation and multiply both sides by 6 or anything. I worked with each expression individually. Doing proof, you can't use the rules of setting up an equation and using algebra, but you can work with one expression at a time. 2k times 2k squared plus 7k plus 6. Let me fix that. So this inside here is this times this k plus 1 is there. So that'll be 2k squared when I multiply out these two things up here, plus 7k plus 6, and all of that is still over 6. And I look here, and I look here, and I have the same thing. I've finished my proof. So the algebra, you probably haven't seen any algebra in a little while like that, maybe. Hopefully you're not like, really concerned about fractions at this point, especially when you're just putting something that's over nothing over 6. But you should make sure you're very familiar with that for this proof by induction. It's an algebra algebra's a requirement for this course, so it's fair to have you do that. And it would be good if you brushed off those cobwebs if they are there. Let's go on to the next example. Now this one is similar, only instead of squaring, we're cubing. So we have a different formula, n squared times n plus 1 squared over 4. And again, it starts with 1. So stop the video and show that p of 1 is true. Okay, you're back. I assume you did that. Now, you may not have, but I'll never know. But, it'd be easier, it'd be better for you if you started doing this a little bit on your own. So p of 1 is true. So when I only have one term, I get 1. Now, when I use the formula, I get 1 squared times 1 plus 1 squared all over 4. So I get 1 times 2 squared is 4 over 4, and I get 1. Okay, so that works. First, if that step doesn't work, you're done. You say, not true. And remember, when you're proving something, you're trying to verify it. You're trying to say it's valid or not valid, similar to what we did with truth tables and implications and arguments. So now I basically rewrite P of n, only I'm going to use K, and I have to add the K plus first term. Well, what's happening to each term here is it's getting cubed, so I have to add P of K plus 1 cubed. I have to write that, and then I have to show that that's going to be the same as if I just put K plus 1 into the formula, because this will be the sum of the cubes of the first K integers, and now I'm going to add the cube of the K plus first. That's the same as saying the sum of the cubes of the first K plus 1 integers, which is what this formula will do if we use K plus 1. So I have K squared, I have K plus 1 squared, and divided by 4. And I'm going to add K plus 1 cubed. Now, the formula, if I replace all the n's with, this is using the formula replacing all of the n's with K plus 1. So the first n becomes K plus 1, and that's squared. The next n becomes K plus 1 plus 1 squared. You can see n squared, it's K plus 1 squared down here. I replace the n with K plus 1. I get K plus 1 plus 1 squared. I wrote it out this way so I don't make a mistake. Students often make a mistake in that part. So what you end up with is K plus 1 squared times K plus 2 squared over 4. Now in this case, in the last case, we ended up working with the part B and rearranging the algebra. Here we're going to start up here. We're going to start with part A and rearrange this algebra. So the first thing I have to do is, notice I have a single fraction. I'm trying to show this single fraction is equal to this sum of two terms. I want to write the sum of two terms as a single fraction. So I'm going to put a 4 here and a 4 here. And then what I see is I have a common factor of K plus 1 there, a common factor of K plus 1. Oh, squared and cubed. The common factor is actually K plus 1 squared. So what I get, and I'll write over here, I didn't leave myself enough space really, is I'm going to factor, so this can all be written over 1, 4. K plus 1 squared times, and it's all over single 4 once I K squared, plus, if I took K plus 1 squared out of this cube, it'll leave me one of these. So I have a 4. So the K plus 1 squared is on the outside. I'm left with the K squared from that. This, I took 2 of them outside. I'm left with that because I wrote the K plus 1 squared out here. That's really what I'm doing. 4 times K plus 1. And all of that is over 4. So I look at what I have here. I have a K plus 1 squared there. That's good. I have a match. If K squared plus this can be written as K plus 2 squared, then I have finished my work. And let's see, I'm going to erase a little bit here. So stop the video and write down anything you didn't catch yet. I'm going to erase some of this. So I have a little more room to work. And that needs to go too. And what I'm going to do next is I'm going to keep my K plus 1 squared because that's already in the form. I already have one in the thing I'm trying to match. So use the problem to guide your algebra. Don't just say, I don't know what to do. You're trying to make this look like that, and you're pretty close. Then let's distribute the 4 and see what we get here. I get K squared plus 4K plus 4. Sorry, I forgot the K. I'm talking and writing too fast. K squared plus 4K plus 4 when I distribute that 4. And what do you know? K squared plus 4K plus 4 does factor to K plus 2 squared. So these two things are equal. So you are done. Now you could write out this last step to make this look exactly like that. But this, the two steps, step 2A, where you go up to the kth term and then add the next term manually, is the same as if you just use the formula to do the cubes of the first k plus 1 terms. That's what you're showing in proof by induction every time. It takes a little practice, but once you write it down a few times and do a few of these, the working with the fractions comes out the same all the time. It's not ever any different than those 3 steps. Okay, so hopefully that will help you with your assignments and with your understanding of proof by induction. And email me your questions. Thank you.